So very good morning to everyone, and I'm grateful to the organizers and convener, Professor Tarak Deb, and also to ICTS. So as you can see that the title is the basic introduction. So I would keep my discussions at very elementary level, at the level of master's students. Okay? So it's not for the experts. Spin orbit interaction in atomic physics. So I would cover in some detail atomic physics part, and then I would try to connect what we understand in atomic physics as spin orbit interaction. How does it translate into the optical domain? What is the connection? What is the analogy and the differences? Okay. So I have organized my talk in two parts. So part one, I would introduce classical concept of angular momentum, then quantum concept, what is called orbital angular momentum, spin angular momentum, and how they are represented by rotation matrices, rotation probes. Then spin orbit interaction in atoms. This part I will cover in some detail. And relation to Berry phase of spin orbit interaction, atomic spin orbit interaction, how does it connect to geometric phases or Berry phases? Okay. And part two, so I would go side by side. I would try to connect this orbital angular momentum, optical angular momentum, orbital and spin part of the optical angular momentum. In fact, optical angular momentum is well known. You can find in almost all the standard textbooks, Landau-Lipschitz relativistic quantum mechanics books, and also Cohen-Tannoudji's book. So optical angular momentum is not a very new thing. So what is new, I would emphasize that. So when you separate optical angular momentum into orbital and spin angular momentum, how they interact between them. That is, and how the experimental realization of these aspects of optics, that is the new. That development took place last 30, 40 years. Okay? And spin orbit interaction of light, this briefly I cover because many other speakers will cover this part, and relation to Berry phase, this is also covered briefly. Okay, so what is angular momentum? It is the motion, angular motion. So you can, this is the standard picture I took from Sakurai's book, that if you have, rotate an object along its z-axis, so we, by pi by 2, so we call it rz pi by 2 and operation. So then it will look like this one. Okay, this part will go because you are rotating in the anti-clockwise direction, so it will look like this. And then again, if you rotate it by pi by 2 along the x-axis, then it will look like this. It is easy to imagine. Okay, and then if you, in the reverse order, if you rotate it along the x-axis first, then it will look like this, and then z-axis, then it will. So you can see that in the reverse order, they are not the same. So this is the pictorial demonstration of what is called non-commutativity. So when the two things, the final results are not the same, we say that these operations are not commuting between themselves. And in mathematical language, then we call, these are some operators, Rx by some, you can represent in terms of matrices. And so we introduce these rotation matrices. We'll go in detail. And so what are their mathematical form? And they act on what in case of mathematical formulation of angular momentum? So instead of this rigid body, if I consider, say, a single particle here in three-dimensional space, okay, then I can represent this. Suppose this is x-axis and this is y-axis. And rotation means this is suppose r, and z axis is along this perpendicular. Okay, so rotation means this r vector, this the modulus or the magnitude remains the same, and you rotate it in the anti-clockwise direction, positive direction. So you get this. So suppose this is phi, and this is phi prime. So then you relate this rotated. Suppose this is x, y, z. So if I rotate it along the z axis, the z remains the same, only x, y changes. So then we said that x changes to x prime and y changes to y prime. So if I write it in a vector form, z remains the same. So z, I am not putting it z, will remains the same. So this, how do they? It is easy to calculate because if you, so this is x and this is y, and then you have this y prime and you have x prime. So this will be, it is easy to calculate cos theta minus sine theta and sine, sorry, this is phi, phi, sine y and cos y. This will be related to x and y. Okay. So similarly, you can so this is the rotation matrix, which is r, z, and you have phi. So this is rotation. Okay. And you can consider that anti-clockwise, the particle is rotating anti-clockwise. So you're looking at the particle from your frame of reference x, y, z. Instead of considering this, you can rotate this coordinate frame. Okay, it was anti-clockwise. You rotate it in the clockwise direction, x prime, y. This is okay. This is y. This is x-axis. So you can rotate it in the different direction, and then you look at this coordinate rotation from the point of view of the particle. So this axis then remains the same. And you will get the same results. So rotation means the frame transformation, rotating frame transformation from one frame to another frame. These are very simple things to understand. Now you are rotating only the frame of reference. Yes. Phi is the original angle. This should be 5 prime, sorry. 5 prime, okay. Okay, you are right. This is, I'm rotating with 5 prime. And so this should be 5 prime. Okay. Yes, change. So then if you consider 5 prime is small in the sense of calculus, infinitesimal means small, then you get basically the angular momentum. Okay, angular momentum operator, okay, it's small, with a prefactor, okay. So angular momentum operator is the generator of the rotation, that I will come back, okay. So you are right that I did a mistake, it should be 5 prime. So in case of 5 prime is some delta phi going to 0 limit, then this rotation matrix will reduce to angular momentum with some prefactor, okay, that I'll come back to that. So the important, so these are very elementary level. Now the important point here, suppose this single particle is not here, we are rotating this radial vector. Suppose particle is sitting right at the origin. Okay. And so particle is not rotating. Now here we have seen that it is equivalent description whether you rotate the particle, whether the particle itself is rotating or not, and if you rotate the frame of reference. So angular momentum arises due to the frame transformation from one frame to the another frame. Okay. In this case, of course, this frame is not what is called inertial frame because it is rotating frame. Okay. And suppose particle is sitting here. And so, of course, this rotation of the radial vector does not arise. What you can rotate here is this x-axis and this is y-axis. Okay. And you can rotate this x-axis some phi prime or suppose delta phi. Okay, some delta phi. Again, it remains orthogonal x-axis. Now the question arises, what will happen to the particle? If you look at the particle, it is at rest in this frame, and you are rotating only the coordinate frames. The particle still remains the same. Is there any change in the particle? What will happen to the particle? If I measure the particle, then the question is this particle position is still 0, 0, 0 particle. What am I going to measure? What am I going? Now here comes the quantum mechanics. I'm measuring the state of the particle, quantum state of the particle. Okay. And quantum state of the particle, will it remain the same if I look at the quantum state of the particle from this unrotated frame and this rotated frame x prime, y prime? Okay. Will it remain the same or will it change? What is the answer? Anyone? Anybody? It will change. It may change, it may not change. Okay, the answer is this. In one case, it will change. In another case, it will not change. If particle is a scalar particle, it does not have any spin, the quantum state will remain the same. Okay, whatever the way you describe. And so the spin of a massive particle itself is a non-classical concept, quantum mechanical concept. Also, it is a relativistic concept because it depends on which frame of reference you are looking at the system. So spin is the intrinsic angular momentum of a particle in its rest frame. So this is the definition of spin in quantum mechanics. So spin has no classical analog in this definition. Okay. So we go to yes. Coordinate frame. But the particle is static. In this case, I'm considering only small rotation, just a certain angle. So then the quantum state of the particle with spin will depend on this delta phi, the angular angle of state. Now, in this case, I'm not considering continuous rotation of the frame. I'm just rotating. I'm looking at the particle from unrotated frame and rotated, then okay, and how they relate. So this is, then it comes the spin matrices. Okay, so the spin operators act on the spinor domain. We need to introduce some other domain apart from this x, y, and z. And in three-dimensional space, orbital angular momentum acts. But they follow the same type of commutation relations. So as far as connecting the states in one frame to another frame, and if you do frame transformations, the rules of game are the same. That's why you can add orbital angular momentum with spin angular momentum, vice versa, because so angular momentums are described ultimately in terms of operators or matrices. So in classical, what is the classical concept of angular momentum? So in classical mechanics, we start with this Poisson equation. Actually, this this okay, here we are. Something, if somebody can educate me on this. Okay, here we are. So this, suppose I'm considering any function, classical function of standard variables, canonical variables, say QP. It could be X and P, or X and PX, or many generalized variables. I'm considering functions, and I'm measuring this function in one frame, and then I rotate the frame, or in another frame it is, so original frame is QP, and then I have rotated this, the change. Then in classical mechanics, the two functions are related by this, while alpha is a small quantity, infinitely small in the sense of calculus, that alpha is small. Okay. And then they are related by this, what is called Poisson bracket. What is Poisson bracket? You can recall that if I have G and F, and this F is called the generator of that change. It is called, so in case of angular moment, in case of rotation, if you rotate to frame, F would be the angular momentum. So definition of angular momentum is it is the generator of rotation. And same definition holds for spin as well as orbital angular momentum. And this is given by del Q, del P, and you put here G and F, and you change this del Q. Here you put F, and here you put del P, F, if you change. This is the definition of what is called Poisson bracket. And then, so in this definition, you can see that Hamiltonian is the generator of time evolution. Okay. Similarly, momentum is the generator of space translation. And so F is the generator. And in case of quantum mechanics, how is it, does it generalize to? So then if you consider F as the, in this case, the Z angular momentum, Lz, then from this, one can easily show, it is a very elementary calculation, that actually this F is the generator of rotation. This rotation matrix is the same rotation matrix here. If you consider this phi is small, okay, then this is 1, 1, this will be minus delta phi, this will be plus delta phi. And you can see that in this case, then alpha would be delta phi, so it matches exactly the same. So now you have proved that angular momentum is in fact the generator of the rotation. Okay. And same is the for x-axis, you can consider rotation x-axis, y-axis, and z-axis. So this is all about classical concept of angular momentum. So quantum concept of angular momentum. So it is again the generator of rotation. So rotation in case of spin, then it will be rotation in the spinor domain. And so this, then in the quantum mechanics, you make a transition from quantum. So this should be replaced by, this was earlier Poisson bracket, and it will be then commutator, G and F, but with, to match the dimension, there will be 1 by I cross. So this I, when you introduce this I, and this quantity then becomes commutator. And when you introduce I, so these generators, they become unitary operators. Okay. I mean, not the generator, the rotation matrices. Okay, these D matrices. And in general, that also one can probe quite easily, because here you have first order, you have retained only first order. If you retain higher orders, because this is a phi prime delta phi is quite small, then you can show that this is the rotation matrix. In general, it could be Rz, Rx, Ry, and this is a unitary operator. In case of Lz, this is like this. So in general, if you consider any direction, any unit operator, n unit operator, okay, in any direction in space, then the rotation matrix is given by this e to the power. So this is in this L becomes a matrix. Okay. So when you in quantum mechanics, when you this commutator, you divide it by h and replace this Poisson bracket in terms of commutator, then what remains are all the matrices which are dimensionless. So you get rotation matrix, and they follow certain rules, group theoretical rules. You can add different matrices, and then you get the whole angular momentum algebra, okay, in terms of commutator algebra. So this is all about classical and quantum concept. So in case of rotation matrix, you can describe in terms of this Euler matrix, Euler angles, and these commutation relations you can put it in compact form, J cross J equal to Ij. So these are the commutation relations, and you have in general a rotation matrix. You can this Ly, and it is sandwiched between two Lz. So if you consider that the wave function of angular momentum is a simultaneous wave function of Lz and L square, because L square is a constant of motion, because it is constant of angular momentum. Conservation of angular momentum is related to the isotropy of the space. Okay, so if for a closed system, okay, if an open system it is not the case, then you have to enlarge your space. Okay, so this is just to recall what we have learned in quantum mechanics. The rotation matrices satisfy all the group properties. So this one can prove this by doing iteratively the commutation relations, using commutation relations. A rotation matrices describe transformation properties from one frame to the another frame. And spin rotation matrices describe also transformation, but one fundamental difference: the spin will not act on special functions or on any space, the space we understand, the three-dimensional space. It will in another space which is called spinor domain. Because so this has the origin in relativistic concept, because spin is the, as I said, is the intrinsic angular momentum of a particle at its rest frame. So this is when we will discuss the spin orbit interaction in atomic physics, then you will understand that what is a spinor domain. Okay? And spin operators obey the similar commutation algebra, and that leads you to add spin with orbital angular momentum. Two or more angular momentum, including spin and orbital angular momentum, can be added. And angular momentum of atoms and molecules. So eigenfunction of orbital angular momentum is, you can describe in terms of this spherical harmonics. This L is a conserved quantity. If you don't have, if system does not have any spin or any other angular momentum, only the orbital angular momentum, closed system. L square, this Lx square plus Ly square plus Lz square. L and M is the projection of L along the Z axis. So Z axis becomes then quantization axis. So if you have a prepared axis in your system, for example, you can apply a magnetic field and it will give a prepared axis, because magnetic field is proportional to the angular momentum always. So this is so coupling between an angular momentum to magnetic field, actually coupling between two angular momenta. So, and you have L, so it gives you L dot S. Simultaneous eigenfunction of Lz with eigenvalues this and M. So the same applies to spin S. Okay, but spin S can have odd half integral values, half spin, which is not allowed in case of orbital angular momentum. Okay, so spin 1, you can have a classical analog, but spin half or 3/2 does not have any classical analog. So as you know, that structure of atoms and molecules, they can be described in terms of angular wave functions and spin orbit interactions. So next we'll come to spin orbit interactions. And this angular momentum algebra gives selection rules. So it is very important to understand angular momentum algebra from the first principle to understand the selection rules that operate in atomic and molecular physics. And that is. Now we come to the main topic, spin orbit interaction in atoms. So in atomic physics, spin orbit interaction is introduced in two ways. They are alternative ways, but they are not equivalent. So one way is by solving Dirac equation. So Dirac equation is a relativistic equation for massive particles. Okay, and Dirac equation. Dirac, when you solve Dirac equation in Coulomb field or any Dirac, central field, Coulomb field is also central field, then you get, and perturbatively, and in the first order perturbation, you get L dot S term. Okay, and by considering interaction of electron spin, and another way, if you consider that electron has spin, so you assume that in electron, where does it come from? Don't bother about that, but suppose electron has spin and it has spin magnetic moment, then you do Lorentz transformation, because then electron will see that the nucleus is moving around itself. So nucleus has a positive charge. For example, for hydrogen, proton is moving, so proton has a moving particle and will generate a magnetic field. So that magnetic field has origin in this Lorentz transformation and of course a relativistic origin. And then you consider minus mu dot B. You consider that mu dot this B minus mu dot B, and that will give you L dot S term. Are they same? Yes.
Are you working now in L4?
Yes, yes, yes. I'm not going to detail, but just yes. In that case, yes, it is the Lorentz transformation, but I will not work out all these details. So if I go to the next slide. Okay. So first, let us focus on the first method, which is the most rigorous one, and it gives correct L dot S term, spin orbit term. So electrons, for an atomic electron, so what is the value of average velocity by speed of light, average speed of in Bohr's first orbit? It is alpha, fine structure constant. It has value 1/137. So it is the speed of electron in the first Bohr orbit, just 2 orders of magnitude smaller than the speed of light in free space. So that's why you can do perturbation calculation. In fact, the entire atomic physics is built on first order, mostly first order perturbation, because you have a small parameter here, which is alpha. And interestingly, alpha depends only on the fundamental constants. And electrons in atoms move with relativistic speed because 10 to the power -2 of C is a huge speed. Okay. So of course, then you have to consider relativistic quantum mechanics here. The relativistic quantum mechanics, so in relativistic particle, when it moves with relativistic speed, so you have this Einstein relationship, energy, and this is you introduce in rest mass. Okay.
So from this picture, you can move to photon picture just by clicking. This response is going to
M0, because rest mass for photon is 0.
Can we switch from this picture to photon?
It can be done, but then it is a vector field photon. So since this is a vector field, then spin will have value 1, not half. Okay. So I will come to that. So that's why I'm so then you go to quantum mechanics, you will replace these familiar operators, and then you get relativistic wave equation, which is called Klein-Gordon equation. And this is then wave function. So when you consider P as operator, and then you get an E also operator, okay? Then you get second order wave equation, relativistic wave equation, second order in time and second order. Because electrodynamics, all the equations are first order. You can go to second order but it's also it has both first order equation, second order equation, wave equation, second order. So you want to construct an equation for massive particles with spin, which are first order in derivative, in time and space derivatives. So that was the original motivation of Dirac to derive this. So you would derive coupling of spin. So spin, these are familiar Pauli spin operators, all of you know, so I'm not going into details. So these are just 2 by 2 matrices. Okay, they are unitary, they are matrices. And if you construct this, so this is you can get this relationship A dot B. So then P square you can replace sigma dot P sigma, these are the same. Okay. But they don't become same when you split into 2 equations. Okay. Then you have, so this is quite easy to follow, because if you pull out this M1 M0 C square on that side, and then you take this P square by C square on that side, then you get these 2 equations. And then you say that, of course, then this equation, since you have here 2 by 2 matrices, so this is 2 by 2 equations. So it has component. So you cannot describe this equation just by a single component wave function, just two component. But you go to the 4 component wave equation. Okay. If I press twice, then it works. So suppose let this part, this one part, I say that this is a wave function phi, and then I put it in another in this phi. We replace this part by phi, then you get another equation. So you can, so a second order equation is split into 2 coupled first order equations. These are coupling. So what is the coupling constant here? You can see that I can write these 2 equations. Coupling constant is rest mass. So if your rest mass equal to 0, then the 2 wave functions psi and phi, they become decoupled, independent equations. You can see that. Okay. So what happens if M0 equal to 0? Okay. Then E becomes equal to Cp, and if you put then this sigma dot P, these are P is unit vector, P hat unit vector, then it can have it is +1. Okay. And in another case, in this case, and for psi case, M0 equal to 0. So psi has positive helicity, that is spin is parallel to the momentum. And for phi, this another component wave function, spin is anti-parallel. So spin can have 2 values in case of two orientations only. So these are called helicity states, this phi, psi, and phi. Okay. And but the other conditions, m0 not equal to 0 for massive particles, then the general state would be then the mixed state, mixed parity state. So we have to construct the equations for mixed parity state. That becomes then standard Dirac equation. Okay. So from the Klein-Gordon equation, we did not do much. We just written in different form. But when we introduced this helicity states and these mixed helicity states, they have different forms. So we have now come down to the first order equations only. And you have then two coupled first order equations. Okay. And these two coupled first order equations, one can construct a 4x4, these are 2x2 psi and phi. And if you construct 4 component wave functions, then this you can write down these two equations in one form. With this one is 2x2 unit matrix, 0 is also 2x2 unit matrix. So then you can write it in this simple form. C alpha, you introduce another matrix alpha, because this beta 4 is this equations. This one, it is actually a 4x4 matrix written in compact form, 2x2 matrix. This is 2x2 unit matrix. This is 2x2 minus 1 in the diagonal term. And then you can have this kind of. So this is actually relativistically invariant, because if you change, because it has 4 components. Because if you, so this is, I have written it in the form of eigenvalue equations, but if you replace this E as IH cross del del T, so then you have space part and space derivative and time derivative, they are linked by first order derivatives. Okay. So this beta 4 is the analog of Z component of the spin in the relativistic case. So you have 4 component. Okay. So beta 4 looks like sigma Z. Sigma Z, you know, the 2x2, 1, 0, 0, minus 1. But here this 1 is replaced by 1 by 1. Okay. And then, so this is, we have considered spin half particle in a central potential. In this case, it is Coulomb potential. No, Coulomb potential we have not yet introduced, but this is, we have considered only in free space. So you can have solutions of this in free space case. And so these are the solutions. So we can consider solutions for free particle Dirac in 2 cases. One is m0 equal to 0, it is massless Dirac particle solutions, and m0 not equal to 0. Suppose m0 not equal to 0 case, we have these equations, and if you have m0 equal to 0, these are the solutions for m0 equal to 0. m0 equal to 0 means so this is we are considering p equal to 0, m0 not equal to 0 case, p equal to 0. So p equal to 0. So we are considering the rest frame of the particle, massive particle. So in the rest frame of massive particle, there is no momentum, there is no space translations. So there is only that time variations of the state of the particle. So this time variations, you can have 2 different solutions. One is sigma will oscillate minus these equations, minus m0 c squared by h cross oscillations. Another would be this plus m0. So this is called positive energy solution. This is called negative energy solution. The positive energy solution is what is we associated with electron. Yes. Yes, that can be. Yes, that can be done. That can be done. Yes, yes. Okay. And so in on p equal to 0 in the rest frame, you have 4 solutions actually. 2 solutions for positive energy, negative energy, and 2 for spin up and spin down solution. This you can write this. The important point for our purpose is relativistic analog of sigma z-axis. In this case, then it is in the rest frame, it is in the spinor domain, because you have spin is there, spin up, spin down. Okay. So it is, even if it is in the rest frame p equal to 0, it is sitting, the particle is sitting right at the origin. Still, because of you have spinor domain, so this is the identity of particles. In elementary particle physics, each particle has either spin 0 or non-zero spin. So that will identify. So if you spin 0, these are scalar particles. Spin non-zero vector particles. So this is you have then 2 classes of particles, bosons and fermions. So
What would be the example for Rashba?
rest mass 0, then you got to like photon pictures. It will be equivalent. In half. Oh, that we have discussed already. Then you have 2 helicity states. In this case, atomic physics. Physical system, then it's difficult to say. I mean, massless Dirac particles. So people think about in condensed matter many other, but I'm not familiar with, because as we know, most of the particles have with mass have spin half particles. Most of them have mass in reality, massive particles. Even neutrino has mass. Okay? It could be, because that is a research topic that I cannot, definitely I cannot answer that. Mishkat, you can comment on. No comment. Okay. So the important point here for our purpose, spin orbit interaction, when mass, when p equal to 0 in the rest frame, the spin states, they oscillate with relativistic frequency. So in case of electron, what is the rest mass of the electron? Anyone? Rest mass of the electron? 0.5 MeV, roughly 0.5 MeV. So it's a huge energy. And if you put here 0.5 MeV, it will oscillate, I think, of the order of 10 to the power 19 or 10 to the power 20 Hertz order. Typical this atomic in a hydrogenic electron, it rotates at the frequency of 10 to the power 14, 10 to the 13.6 electron volt, if you consider this. So exactly you will see that this is actually difference is alpha square and structure constant. These are optical. In case of hydrogenic electron, so that is orbital motion. So orbital motion, the time scale is 10 to the power 14 Hertz, that is electron volt, if you convert it into. And in case of relativistic particle in electron mass, if p equal to 0 in the rest frame, electron is oscillating at the frequency of alpha square into hydrogenic orbital frequency. So there is clear separation between the time scales or oscillation frequencies in the rest frame and the electrons in the frame of hydrogen orbital motion of the electron. Okay, that has to do with what is called adiabaticity, and here comes the Berry phase. Okay, I'll go. So that's why I have done all this exercise to show that in case of rest frame, electron will oscillate with huge oscillation frequency. And this frequency scale is actually alpha square order. Okay. And okay. Now, solution of Dirac equation with a central potential leads to what is called spin orbit interaction. So I will not go into detail of derivations in any standard atomic physics book or quantum mechanics book. You will find the derivation. Once you know this is a first order differential equation, but this is 4x4 matrix. You can split into 2x2 matrix equations, coupled matrix equations. And in the non-relativistic limit, now you apply perturbation that this relativistic energy you split into the rest energy and some E prime, which is, then you consider this E prime is much smaller than M06 square. So in fact, we have understood that in case of electron in first Bohr orbit, this is alpha square order difference energy. So this is suppose orbital energy, and this is some rest energy. Then you have, so you can use perturbation, and this perturbation parameter is alpha. Actually, it goes as alpha square order. And because alpha square is of the order of 10 to the power -4, so it is really quite small. So you can cut it in first order perturbation. So that's why in entire atomic physics is built on first order perturbation mostly. Okay. So SY is one of the three terms. So you get three this SY term and other Darwin term and the correction to the kinetic energy of electron. And this one term is you can look at Brownston-Joachim quantum, this atoms, physics of atoms and molecules for derivation. So these are a little lengthy derivation, but easy to follow because these are first order equations. You just manipulate mathematically. And this is the coupling, this part, and this B is the energy. Potential energy of one electron with Z equal to 1 in case of hydrogen, but in general it is this. So then you get L dot S, and S is here you can express in terms of Pauli spin operator. This is half of Pauli spin operator. Okay. So this is one way of deriving spin orbit interaction in atom physics. The second order, that is important to understand the very phase connection. Okay. So this electron spin in internal magnetic field. If we apply any external magnetic field to an atom or molecule or any particle, then if it carries, the particle carries magnetic moment, it has spin, so it has spin magnetic moment, then the energy, the shift would be minus mu dot B. Instead of external magnetic field, you consider that magnetic field is internally generated due to the motion of the proton. Right? So then that magnetic field from relativistic consideration, so this is derived from Lorentz transformation. This B is related to the velocity. In this case, velocity of proton, because I am looking from the frame of reference of the electron to proton, because proton is generating this magnetic field at the position of the electron. So this is given by this B. And E is a radial electric field. So this is electric field of the proton. So that's why you have proton. Okay, this is field. So this can be written in terms of this potential energy of electron, and then you have V is, of course, you can replace P by M. But this is a semi-classical and ad hoc method, because here you are making many assumptions that electron has spin magnetic moment. Then you are applying this classical mechanics of relativistic mechanics transformation. And then you are replacing this P by operator if you consider operator. Okay. And this mu, we know that this is E by twice M S, and GS is gyromagnetic ratio, which is 2, roughly 2 it is. So then you get this expression. So if you compare the derivation of this method and the earlier method, there is a factor of 2 difference. So this H prime we have derived by second method, ad hoc method, which is in many books they derive, but even in many books the authors don't derive using Dirac equation. They say that this is, but here it is not very rigorous derivation. The rigorous one is this, the earlier one, and then you get, there is a factor of 2 difference. In this case, this GS, there was no GS2 earlier case. This is the correct one. So then you have to correct this. So where did we go wrong? Because it is, you are applying this Lorentz transformation, which is the inertial frame, but it is not inertial frame. And this has to do with what is called Thomas precession. And Thomas precession, as I said, that electron in its rest frame will oscillate as a huge frequency. Okay. So there is a clear separation of time scales. And I'm not going to detail that because that is some tricky point. But if you then if you consider Thomas precession, then this factor 2, there will be a half factor and it will be exactly the same. And that Thomas precession, that correction term can be calculated. Okay. And so what is Thomas precession? What is origin? It is related to this adiabaticity and Berry phase. So adiabaticity, if you consider this orbital motion of electron is slow motion, slow variables in comparison to the spin motion, because spin is the intrinsic angular momentum rest frame, but it is oscillating in its rest frame with relativistic energy. And because there is difference, so while considering this spin motion, you can consider the orbital motion as some parametric dependence on the spin motion. Then you can calculate in this way also, and then you can. So what is Berry phase connection to SY? So this could be important for our later discussion. So this spinor of electron and its rest frame oscillate with relativistic frequency, which is 0.5 MeV. And then orbital motion of atomic electron has characteristic frequency. Suppose if you consider electron in first Bohr orbit, then this is, of course, you know that 13.6 electron volt. And then there is of the order 4 order of magnitude, as I said repeatedly. And then in 1991, Harsh Mathur, so he showed that if you consider Berry connection and Berry phase in this case, then this Thomas precession can be accounted for considering the Berry phase. Because when there is spin motions and there is orbital motion, the orbital part is slow part, because then, so I'm not going into detail, I am just considering this qualitatively. Okay, you can go through this paper. So then comes Pancharatnam Berry phase connection to spin orbit interaction. Okay. So it is built on adiabatic theorem. In a system, if there are 2 sets of variables, one set is slow variables and another set of variables are fast variables, in this case, for example, then you can calculate the motion due to the first variables only, considering that slow variables are the dependence of the first variables on the slow variables is parametric dependence. Okay, so then you solve eigenvalue equations, and eigen functions and eigenvalues, they depend parametrically on the slow variables. So these people in the molecular physics community, they use, since that Born-Oppenheimer approximation, Born and Oppenheimer in 1930s. So always they do that, and that's how we calculate molecular.
Eliminate the first variable,
Yes, if you eliminate, then first you first calculate the first variables quantum mechanically, and then you trace out the first the wave function of the first variable, because initially you consider slow variables just classical variables like, and then you introduce quantum mechanics, or so you find the solutions due to the first variables. So that's how. So in this case, then you encounter a phase which Berry showed. First, Pancharatnam showed in polarization, photon polarization, what is called the parallel transport. Parallel transport is if you have a sphere and if you transport a vector on the sphere, and locally you consider that this is the radial vector of the sphere, and that vector and another that they construct a triad of orthogonal basis. You remain that orthogonal basis and you transport this so that this vector does not twist around the R vector, okay, this radial vector. Then if you closed path, if you transport this in a closed path in a sphere, in any, you will consider any sphere, any closed path, then you will you can find that the original, if you bring it with a closed path from the initial position to the final position, the same position, then there will be a vector will not point in the same direction as the original direction one. The vector will, there will be a phase difference. So that is the Pancharatnam phase. Pancharatnam in a particular system, the polarization of light. Okay, in case of if you change slowly the polarization of light, polarization state, then you get Pancharatnam. Then Berry generalized it for quantum systems. Okay, and then you get Berry Pancharatnam phase. Okay. So this Berry phase is not a dynamical phase, because the dynamical phase depends on the dynamical variables integrations over time, but it is in the parameter space. You get this e to the power, suppose I gamma is the phase, then gamma would be related to some vector dot some parameter, any parameter, say d phi, and then you integrate over closed path over phi, and then you get. So this parameter could be any parameter. In case of molecular physics, then this parameter is the internuclear distance, internuclear vector, internuclear. Okay, and the first variables are the electron variables. Okay, and this is this depends only on the geometry and the path on which you calculate this closed integral. Okay, and then this has connection with the gauge fields. Okay, you can consider this some gauge field, and then because, and also you can connect it with some curvature. Okay, so that part I am not considering in detail, but what Berry showed most importantly, that if you make a gauge transformation when you consider gauge this like a vector field, if it depends on the position variables, then it is like a vector field, and this you can make a transformation. You can choose gauge. Okay, you can, because any vector field A plus some gradient of a scalar, you can make another vector field, and then curl of that will remain the same. But curl of what is physical, what you measure, that is the field. So this is called curvature, and this is called the connection, Berry connection. Am I right? Berry connection and curvature. So curvature is what matters in physical realization or in measurement. Okay. So this Berry showed that this is gauge invariant. This parameter. So in order to make it gauge invariant, then this when you make this transformation, A going to A plus some gradient of some chi, okay, then white one will do, I think. White, I don't see what. Okay. Okay, so this is what I'm writing, this gauge transformation. You know that gauge, if you add some gradient of some scalar quantity, any scalar function, then magnetic field will remain the same. Magnetic field is equal to curl of A. What is curl of a gradient of a scalar? What is the value? Will it vanish or will not it vanish? It will vanish, but it will vanish in a region, simply connected region. Okay. And if you have multiply connected region, if you have hole in the region, then this will have quantization. It will be quantized. So if it is quantized for is transformed twice pi and pi and gamma, then e to the power, when you make e to the power I gamma, then it will e to the power I, suppose this is gamma prime, so it will be again e to the power I gamma. It will remain the same. Physical, I mean, physical realization will remain the same. It will not change. The measurement values will remain the same. So this is what Berry showed. And what is the connection with the Berry phase? That part probably Nirmalya will cover in this evening, and also Professor Dutta will cover. But this is in a nutshell what we understand the Berry phase. Okay. So slow versus fast degrees of freedom. I said that set of variables. You can say that set of degrees of freedom. So the Born-Oppenheimer approximation is so. In fact, this Berry phase is realized in molecular physics, and molecular physics community, they often use this Berry phase connection, particularly for trimer, this what they call conical intersection. In fact, before Berry discovered this famous Berry phase, there were very important papers on molecular physics. All cited that they considered this kind of phase change in molecular physics. And geometric phase, because it is closed integral in vector space, it depends on the path and not on the geometry, but not on any dynamical quantities. Vector function leads to gauge structure, as I showed here, that it loads. So it is not necessary that the gauge field will arise only from the charged particles, only in case of electromagnetic. So that's why this Berry phase connection is most important. It is quite theoretically, it is quite general. Whenever you have Berry phase and curvature connection, then you can get equivalent vector field, equivalent gauge field. And that's why people consider the gauge field for neutral particles also. In case of say cold atoms, Saptarshi may be interested in, because they call it synthetically induced or synthetic gauge fields. So gauge field and Berry phase connection, that makes it quite general. And geometric phase is gauge invariant. That can be shown that we have already proved this, that this is gauge invariant, because this gives you the Berry's connection curl of a vector or the curvature. So okay, I have how much time I have? Another 15 minutes. So 15 minutes, I will, including discussion. So I will try to cover this and summarize this. Okay. So now we come to optical angular momentum. So a few initial observation. What is optical angular momentum? So light carries linear momentum, and light carries also angular momentum. Of course, then polarization is related to the angular momentum since 18th century or 19th century, because there is a back experiment that the polarization of light can be exchanged to material particle, and that will lead to this rotation of the disk. Okay, so it is well-known fact, experimental fact, that light carries both linear momentum and angular momentum. What is new in this case then? So in case of paraxial approximation, when you consider that all the light rays are almost going in along one axis, and light, the vibrations, so electric field vibration, magnetic field, transverse, okay? And so wave vectors are almost all the wave vectors. So wave vectors, you can consider this as linear momentum. So linear momentum, all the are along one direction, then this is axial approximation. And then you can split the total orbital angular momentum into total angular momentum. We don't say orbital or spin, we call it optical angular momentum. In fact, in Landau-Lipschitz relativistic quantum mechanics, they call optical angular momentum. Then in Guwahati's book, also optical angular momentum. So this is the well-known optical angular momentum. Does it have well-defined orbital angular momentum? Does it have also well-defined spin angular momentum? Yes or no? That is the discussion, part of the discussion. And that field has developed over the last 30, 40 years. And in general, spin and orbital momentum are coupled. So that's what we get, spin orbit interaction in light. But under certain circumstances, experimental conditions, you can separate out, almost separate out spin and orbital angular part. Then you can say that spin, you can define. So the defining spin and angular momentum is approximate under certain conditions. But in general, it has total angular momentum. Light has linear momentum, light has total angular momentum. So angular momentum of light means angular momentum of a massless particle or photon. And photon has no rest frame. The spin of photon is not well defined in this case. This is not my words, it's the word of Landau and Lipschitz. Okay? So you cannot argue with me, you can argue with Landau Lipschitz. And then only the total angular momentum of photon can be defined. But that is 50, 60 years ago. And then the wave function of photon is this. You can say that roughly speaking, naively, that it is the vector potential. Because the vector potential, it depends on the position variables, and also it is a vector quantity. Okay. So if it is a scalar quantity, then this is like a wave function. Wave function is a function of the position variables. Or if you go to the reciprocal space, K space, then you can define AK is the wave function. So a vector function is equivalent to a spinor of rank 2. Okay. Spin half is a spinor of rank 1. Rank means how many indices you need to specify or define your wave functions, spin wave functions. Okay. So in case of spin half particle, you would need only one index. Okay. In case of, so as we generalize the vector quantities in classical mechanics to tensors, you can generalize spin half particle to spinors of other ranks. So spinor of 2 rank means it's like a vector. The way a vector will, three-dimensional vector will transform from one frame to the another frame when you consider rotation in three-dimensional space. Similar way, the spinor of rank 2 will rotate. And so this is, the spinor of rank 2 means it has spin 1. Because rank of a spin is twice s. If it is 2, then its spin would be 1. Spin half is a spinor of rank 1, so it is twice s. 2 into half is 1. Okay. So in that sense, you can say the photon carries a spin of angular momentum 1. And spin and orbital angular momentum of photon are defined to express transformation properties of the wave function. So in this case, wave function means vector potential, okay, vector field, actually vector field, I should say. The S1 implies that the wave function is a vector, and this OAM, you can define then orbital angular momentum is the order of spherical harmonics in general wave mechanics or in quantum mechanics. But this is spherical harmonics we describe the angular momentum of electron, orbital angular momentum in terms of spherical harmonics. Spherical harmonics are the wave functions, angular wave functions. So there, if you parity, if you change parity, if you make x to minus x, y to minus y, then it changes by -1 to the power L. Okay. Because the wave function is a scalar quantity. Scalar means it is function of scalar function of the position variables. Okay. But in case of then A, it is a vector quantity. So vector will change by 1. So it has parity -1 to the power L plus 1. Okay. Spherical harmonics has -1 to the power L because the vector quantity it has L. So what are the possible states for a given J? So this is also I am following Landau-Lifshitz argument that if you have L equal to J, then parity is given by -1 to the power J plus 1. And L equal to J plus minus half, then it is -1J. So for J equal to 0, total angular momentum is 0. So in here J is, then there is only one state with L equal to 1, with P equal to plus 1. And because AK is a transverse vector, the states that correspond to longitudinal vector are not allowed. Okay. But Professor Subhasish Gupta will tell you that probably that there is transverse spin longitudinal under certain circumstances. So those states have this P equal to -1J. So photon cannot have J equal to 0 state. Photon will, this argument shows that photon with J equal to 0 is not allowed. So photon will have J non-zero. J can be any value, integer values, because it has spin 1, an orbital, of course, then integral multiple. So then, okay. So this part maybe I would not go into detail. These are mathematics. So if we want to derive or optical angular momentum from classical electrodynamics, so force is, you know, that this is a Lorentz force. You have electric part and magnetic part, and you have velocity. The rate of doing work, you can consider this the current density to this dot product. And so Maxwell's equation, you can use the Maxwell's the first order equation. You can replace J, and then you can get this J dot E quantity with this. So these are just a little lengthy but easy to follow calculations. And then finally what you get is the rate of doing work, F dot B. Mechanical part is given by this, and total the mechanical and field energy, these are energy, okay, rate of energy, rate of doing work. So this will be given by the pointing vector, with Carlow pointing vector. So Carlow pointing vector, the pointing vector actually carries spin momentum. Sorry, the momentum density. Okay, so it can have two parts. One is orbital, another is spin. So you can think of this wave vectors, rotation of the wave vectors, slow rotations. So this spin polarization is a fast oscillating variable, and this, if you consider axial approximation. So if you have a spiraling motion, that will give you orbital angular momentum of k vectors. Okay, and then you can follow the Barry's paper. He defines something called optical current. Optical current is different from the simple wave vectors. Okay, so it can have optical current due to rotational motion, rotational current, and due to spin current and orbital current. So then total orbital angular momentum is defined in this way. So again, you can relate it like orbital angular momentum kind of thing, but this is total angular momentum. So this is different from spin as we understand in quantum mechanics in atomic physics. So then you can split it into under axial approximation, orbital part and spin part. So these calculations you can follow in this book, but this vector calculus you can follow Quantanov's book on relativistic quantum mechanics also. And then you can define under certain point orbital angular momentum and spin angular momentum. So spin is associated with the polarization, and the vector wave function reduces to scalar equation of constant polarization for constant polarization, and orbital angular momentum is associated with the azimuthal phase. Okay. So now spin orbit interaction of light. This is the main topic of this discussion. Orbital angular momentum of light arises due to slow rotation of the center of applications of the wave vectors, okay, or the center, okay. So that is because orbital angular momentum has to do with the rotation of wave vectors, okay. And due to transversality condition, then rotation of k vectors, if it rotates like this, then if you impose transversality condition, transverse oscillations, then the polarization, this rotation must influence polarization in some way, and that leads to spin orbit interaction. You cannot have fixed polarization, okay. And slow rotational motion of k vectors may be treated adiabatically while considering much faster spin polarization evolution, and that gives to the gauge structure of the phase that Nirmalya will cover in detail. I'm not going into that, and follow other lectures on this meeting as well as SOP for details of SY. So it has a huge range of applications in spintronics and spin orbit photonics and spin current, and also in quantum information theories, okay? Because orbital angular momentum can vary from 0 to infinity, any L value, and this can carry many information. So with this, I stop here. Thank you very much. Am I on time? Yes.
We still have time for one or two questions.
I think they had many questions, so during.
Explain these two slides which
Which one?
yeah, from here, what? Yeah, what are you trying to say?
Yeah.
Spin in the current being all.
The question is to
So-
explain these last two slides.
So optical currents is described in terms of pointing vector. Okay. So, but it has two parts. One is, of course, you can consider this motion of k vectors and its rotation. And also, you have polarization direction. That two rotational motions will be coupled, and spin is associated with the polarization, and it has spin 1. Okay.
So this OAM states the orbital angular momentum. So by definition, it's continuous variable, right? The orbital angular momentum part of the light, the k vector rotating, and this can go from non-rotating to very fast rotating states. But in principle, it can be continuously variable, right? But you are associating quantum nature.
Eigenvalues are discrete eigenfunction. Because you, as in quantum mechanics
Mhm.
of atoms, the described in terms of discrete orbital angular momentum states L. So if you measure, then you will get discrete values because it will have. So if you prepare a light with angular momentum, say 30.
So I can prepare a light with an orbital angular momentum. Now, point is that when it will interact with atoms, so then means will it have discrete absorption or interaction?
Axial approximation, if you use Laguerre-Gaussian beam, then it will carry discrete orbital angular momentum. So discrete orbital angular momentum will interact with the atoms. But yes.
So if you increase the L number, orbital angular momentum, you can go from the discrete to continuous.
For large
And-
angular momentum.
Yeah. And you can go from the quantum domain to classical domain. Yeah.
That is true for also in quantum mechanics. If you have large, huge number of, so you can describe in almost like classical angular momentum.
I actually have a question.
I have one question. You're describing electrons' orbital motion as a slow degree of freedom. So the parameter that will characterize this slow degree of freedom will constitute the vector potential in Berry phase.
That's what Harsh Mathur showed in his paper.
Okay, yeah, I
Yes.
was actually interested. What will be the parameters then corresponding to
It's
those?
very involved paper, involved calculations that I did not go. But you can appreciate that there is clear separation of because of this alpha square. Okay, so the spin will oscillate at relativistic frequency, relativistic energy of electron, and we know when we calculate Bohr using Bohr's theory, the quantum states of electron in the first Bohr orbit, and we get the orbital states, okay, which have oscillation frequencies of the order of electron volt, and that is milli-electron volt. So in that case, it is connected to very phase and very curve.
Any other questions? If not, please join me in thanking Professor Bimalendu Deb for a very lucid and stimulating